Okay, so yeah. I'm just writing down a few obvious properties of the induced map in homotopy quotients. Okay? And then there is one final one that is not so obvious, and that is if the original map is a fiber bundle with fiber F, then the map in homotopy quotients is also a fiber bundle. Is also a fiber bundle with fiber F. Okay? Now, all of these properties are very straightforward, except for the last one. So I will prove the last one. Okay? And the others you can do yourself, or you can read it in the book. Yeah, how do we show that? Well, you see, you have this map F from N to M, and both N and M maps to a point. Okay, so this diagram induces a diagram in homotopy quotients from NG to MG, and then both of these maps to a BG, the homotopy quotient of a point. Okay. And we know that NG and MG are fiber bundles. Okay, so let's see. So NG over BG is a fiber bundle with fiber N, and MG over BG is a fiber bundle with fiber M. Okay. So that means that every point B in BG has some neighborhood over which both of these are trivial. Okay? Has a neighborhood U over which, now let's call this map pi n and this map pi m. Okay? So pi n inverse of U is homeomorphic to U cross n, and pi m inverse of U is homeomorphic to U cross m. And now this diagram, the commutativity of this diagram says that FG preserve fibers. Right? It sends the fiber over a point to the fiber over the same point. So locally, let me see. Yeah, FG from NG to MG is locally U cross N to U cross M. And because N is locally trivial over M, when you cross by U, it's still locally trivial. Okay? So this, which is a fiber bundle, which is locally trivial, with fiber F. Okay? Yeah. And so FG is locally trivial with fiber F. Okay? Therefore, it's a fiber bundle. All right? Yeah. And then, okay, so finally, I want to answer a question that was raised last time. Okay? So last time we computed the equivariant cohomology of S2 under the action of S1 using a spectral sequence and one of the questions that was raised was why is the bottom row injective, into the cohomology of the total space. So, and so I said there's this proposition that if there is a fixed point, if G acts on M with a fixed point, then the cohomology of BG injects into the equivariant cohomology of M. Okay. So that's what I want to prove now. So if you have a fixed point, then the inclusion map from P into M is a G map. If G is a fixed point, right? If P is a fixed point, okay? If it's not a fixed point, then it won't be a G map. Right? Because when you map on, when you act on P, it could go somewhere else. Okay? But if you have a fixed point, then this is a G map. And, okay. And then you can let pi be the constant map. Okay. Then pi composed with I is the identity from P to P, okay? And now you do functoriality, okay? So by functoriality, when you take IG star, it goes in the other direction. So IG star composed with pi G star is the identity. It's the star of the identity, which is the identity on the pi g star. It will start with the cohomology of a point. Right? Okay, and it first goes into the equivariant cohomology of M, then it goes into the equivariant cohomology of a point. Okay. Okay, and so what this says is that pi g star has a right inverse. Therefore, pi g star is injective. Pi g star from the equivariant cohomology of a point, which is the cohomology of BG, to the equivariant cohomology of M, is injective. Okay? Yeah. Okay, yeah. So that answers this question. Okay? If you have a fixed point, then the cohomology of the classifying space, which serves as the scalars, it injects into equivariant cohomology. Okay? Okay, now, in the rest of the hour, so I would like to prove some general facts about classifying spaces. Okay? Because so far we only know just a couple of classifying spaces, right? We know the classifying space of S1 is CP infinity. The classifying space of Z is what? The classifying space of Z is S1, right? Because the total space is R. And what's the classifying space of Z2? Z2, that's a group with two elements, 0 and 1. Yeah. So Z2, classified spaces. So Z2 acts on the sphere by the antipodal map. You have the sphere, and if you identify the antipodal map, what do you get? Yeah. So if this is Sn, then the quotient is Rpn, okay? And this is a Z2 bundle, right? It's locally trivial. So Sn mapping to Rpn is a principal Z2 bundle. And S1, sits inside S2, which sits inside S3, and so on, as equators. And then the quotient is RP1 sits inside RP2, sits inside RP3, and so on. Okay? So you have this infinite diagram, and then you can just take the union. The union of all the spheres is the same as the union of the odd spheres. So it's S infinity. Okay. So S infinity be the union of all the spheres. And then there is an RP infinity be the union of all the RPNs. And there is a Z2 action on S infinity with quotient RP infinity. Okay? And so, because the S infinity is contractible, so S infinity mapping to RP infinity is the universal Z2 bundle. And so VZ2 is RP infinity. Okay, so we know three examples of classifying spaces. And I'd like to construct more examples. Okay, so the first example is when you have a closed subgroup. In fact, you notice that Z2 is a closed subgroup of the circle S1. And this antipodal map, it's really multiplication, right? Because Z2, you can think of it as yeah, 1 minus 1 inside S1. So 1 here minus 1 here. And so this action, the antipodal action, is induced from multiplication by elements of S1, right? It's just multiplying by minus 1. And it has the same total space for the universal bundle. Okay? That's in general true, because if a group acts freely on a contractible space, then any subgroup will also act freely on the contractible space. Okay? And so we just have to show that if you take this and you quotient out by the subgroup, you still get a principal bundle. Okay? So, yeah, that's what I want to show now. Okay, so we want to look at closed subgroups. Okay, so let H be a closed subgroup of a topological group G. Now, if G acts freely on EG, then so does H. And so now we are going to use EG as our total space, and we let BH be EG mod H. Take the quotient. Now, then okay, so proposition I'm just going to call it B for now because I don't know yet that it's a classifying space. Okay, so then EG of mapping to B is locally trivial with fiber H. Okay, and that's because since EG mapping to BG is locally trivial, so it's locally U cross G, right? Yeah, it's a principal G bundle. So locally it's U cross G. And so now we take the quotient by H. Yeah. So U cross G, and so EG quotient out by H, okay, is locally U cross. When you take the quotient, it acts only on the G part. Locally, it's U cross G over H over U. And so, no, sorry, this is just, yeah, this is a set in here. And then, yeah, so EG mapping to EG over H is locally U cross H mapping to U cross G mod H. Okay. Now, but, and here, this is a somewhat difficult theorem, okay, and it is in Frank Warner's book on differentiable manifolds. which says that if H is a closed subgroup, oh, and now I realize that, yeah, I have to assume that it's a Lie group, yeah. So G, we need to assume that G is a Lie group. This should be a Lie group, okay? And H is a closed subgroup of a Lie group. When you have a closed subgroup of a Lie group, then G mapping to G over H is locally trivial with fiber H. Well, it's more than that. It's a principal H bundle. It's a principal H bundle. Okay? Mm-hmm. So that means locally it is U cross, not U, but some other open set V cross H mapping to V, okay, for some open set V in G mod H. And so therefore, U cross G mapping to U cross G mod H is locally U cross V cross H mapping to U cross V, right? V is in G mod H. And yeah, that proves that this one, that's locally trivial with fiber H. Okay? So EG mapping to EG over H. EG mapping to EG is locally this, and that's locally this. So is locally trivial with fiber H. Okay? And yeah, so that says that you can, we can take BH to be EG mod H. Okay? Yeah. So what this says is that if you have a universal bundle for any Lie group, then you have a universal bundle for any closed subgroup. Okay? So, theorem, if a Lie group G has a universal bundle EG over BG, then any closed subgroup as a universal bundle, e.g. to e.g. mod H. Okay. Yeah. Okay, now another theorem I want to prove is the direct product of two groups. So theorem, yeah. If pi I from EGI to BGI are universal bundles for I equal to 1 and 2, then pi 1 cross pi 2 from EG1 cross EG2 to BG1 cross BG2. So that takes E1, E2 to pi 1, E1, pi 2, E2 is a universal bundle for G1 cross G2. Let's see, I think this one is obvious, right? So G1 and G1 acts freely on EG1, G2 acts freely on EG2, and yeah, so so if you have G1, G2, and it fixes a point E1, E2, oh, so, yeah, right, yeah. Then that means G1, E1 is E1, G2, E2 is E2, and because G1 and G2 acts freely, so G1 is the identity and G2 is the identity. Okay? Yeah. So so G1 cross G2 acts freely on E1 cross EG1 cross EG2. And what's a fiber? Yeah. So pi 1 cross pi 2 inverse of B1, B2. Well, to map into B1, you can take any point so it's E1, E2, where E1 is in pi 1 inverse of B1, E2 is in pi 2 inverse of B2, and that means it's G1 cross G2. Okay? Yeah, okay. So, and I think local triviality is quite obvious too. So anyway, I'm gonna just stop here because it's pretty straightforward. And so the corollary is that the classifying space of G1 cross G2 is the classifying space of G1 cross the classifying space of G2. Okay? well, here I'm using equality in the sense of homotopy equivalence, because up to homotopy equivalence, the classifying space is unique. Okay? And now with this theorem, then, well, we have a lot more examples now. So, we have the classifying space of a torus, right? So, a torus T it's just a product of circles. That's the definition of a torus, and therefore the classifying space of a torus is going to be the product, the Cartesian product of the classifying spaces of the circles, and that's CP infinity. And so then if you have a torus action, the coefficients of equivariant cohomology are in the cohomology of BT. And if you have a direct product, a Cartesian product of spaces, then, and these are, yeah, the cohomology is free, right? So by the Kunis formula, the cohomology of the Cartesian product is just the tensor product. Okay? So this is by Kunis. Says it's free abelian. Okay. If it's not free, then Kunis formula has some other terms, right? In terms of, I think, the torsion. Yeah. So now, okay, and then like each of these is a polynomial ring, ZU tensor. But they're different polynomial rings because they correspond to different circles. So we should put some subscript there. Say U1, UN. So if there are n factors, and the tensor product of these polynomial rings is just the polynomial ring in n variables. Right? There's an isomorphism between these two. Okay? Okay. Yeah, so let's see. Yeah, all right. So now what we need to do is to find a universal bundle for the orthogonal group, because there's a very well-known theorem in representation theory, okay, that says every compact Lie group can be embedded inside an orthogonal group. Okay? So every compact Lie group is a closed subgroup of an orthogonal group. Yeah. Let's see. This theorem, every compact Lie group can be embedded as a closed subgroup of some orthogonal group. Okay. It would be different K for different groups. So if we could find a universal bundle for the orthogonal group, then we have a universal bundle for every compact Lie group. Okay? And a universal bundle for OK it's okay. Let's see how we can construct that. Okay, so last time I defined VKN. That's the orthonormal K frames in Rn. And so an orthonormal K frame can be represented by a n by k matrix. So it's n by k matrix where the columns are orthonormal. Okay. And so you can multiply on the right by a k by k orthogonal matrix. So we can multiply on the right by a matrix A in OK. You know, if you multiply by an orthogonal matrix, it still remains orthonormal. And now if you take the, so this is like the change of basis matrix for this K-plane. So K-frame in Rn spans a K-plane in Rn. Of which it is a basis. Okay? And then multiplying on the right by an orthogonal matrix, it's just changing the basis. Okay? And so if you take the quotient of VKN by the action of OK, it will just give you the K-plane, so it's the Grassmannian. GKN. Okay. And okay, then I have to show that it's locally trivial. VKN maps to GKN. It's locally trivial with fiber ON, so it's a principal OK bundle, fiber OK. Now this is done in the book. And then you see you have this inclusion because Rn is included in Rn plus 1. So you have a sequence of inclusions like this. And the Grassmannian of K-planes in Rn, that sits inside K-planes in Rn plus 1 and so on. So if you take the union over all n, you get the infinite Grassmannian and the infinite Stiefel variety. So let Vk infinity be the union of Vkn over all n. You probably should start with k. And Gk infinity be the union of all Gkn's. Then Vk infinity. Okay, so then you have to compute the homotopy groups, and then you can show that it's all zero, so it's weakly contractible. And it's actually a CW complex, so it's contractible. And so therefore, Vk infinity mapping to Gk infinity is the universal OK bundle. Okay? And so the theorem that is a corollary of this is that every compact Lie group, because it's a close subgroup of an orthogonal group, so it has a universal bundle. Okay? Okay, yeah. Yeah, so there are some details here that you have to check, and that's in the book. You know, it's kind of very straightforward calculations of homotopy groups of the Stiefel variety. Okay, and they're all zero. So I'm going to now, stop here with the topological theory of equivariant cohomology. And what I want to do next is to show that you can compute equivariant cohomology of a smooth manifold using differential forms. Okay? So starting next time, we will assume that all the spaces are smooth manifolds, and the groups are Lie groups, and then we will show how to calculate equivariant cohomology using differential forms, and that will give us the ring structure for the equivariant cohomology of S2 under rotation, because we still haven't figured that out yet, right? Yeah. Okay, so see you on Monday. Okay.